हेलो गाइस, वेलकम टू माय चैनल डेज लर्निंग। आज हमें थर्मोडायनामिक्स के अंदर एक छोटा टॉपिक पढ़ने वाला हूँ। इट इज़ अ वेरी इंपॉर्टेंट टॉपिक। इस टॉपिक के नाम मैक्सवेल रिलेशंस। इस टॉपिक ऑल कॉम्पिटिटिव एग्ज़ाम को सिलेबस में है। नीट, एम्स, जेई मेंस, जेई एडवांस्ड ऑल एग्ज़ाम को सिलेबस में ये टॉपिक इंक्लूडेड है। और इस टॉपिक फिजिक्स केमिस्ट्री को अंडर ग्रेजुएट सिलेबस में है। और इस टॉपिक इज़ ऑल्सो इंक्लूडेड इन द अंडर ग्रेजुएट इंजीनियरिंग कोर्सेस। सो दिस इज़ अ वेरी इंपॉर्टेंट टॉपिक। लेट्स स्टार्ट। इस टॉपिक के नाम मैक्सवेल रिलेशंस। We are starting from the first law of thermodynamics. We know from first law of thermodynamics. From first law of thermodynamics. First law of thermodynamics. From first law of thermodynamics, we know DE equal to, or first of all, I can note down the different thermodynamical parameters like E और U, इसको कहते हैं इंटरनल एनर्जी। This is internal energy of the system. Next, H, it is called enthalpy of the system. Next, G, which is known as Gibbs free energy. Then A, which is known as Helmholtz free energy. Helmholtz free energy. And there are other parameters like P for pressure, S for entropy, S for entropy, P for pressure, V for volume, and lastly T for temperature. So in Maxwell relations, all the thermodynamic parameters are correlated. Now, from first law of thermodynamics, we know dE or du, this is equal to del Q plus del W. And we know dE equal to del Q minus PdV. This is our first relation. We come to this relation from first law of thermodynamics. Now, next from second law of thermodynamics. From second law of thermodynamics. We know del Q equal to, from second law of thermodynamics, we know ds, this is entropy change, equal to from second law of thermodynamics we know ds equal to, from second law of thermodynamics we know ds equal to del q reversible by T. We know we are using all differential parameters, differential terms. So definitely all terms are used in reversible processes. So we can write del q, this is equal to T into ds. Definitely this is reversible. So this is our relation number 2. Now we can substitute the value of del q in equation 1. So substituting the value of del q in equation 1, we have from equation number 1 and 2, we have dE equal to TdS minus P into dV. So this is very important relation. This is very important relation, D equal to TdS minus PdV. So this is our relation number 3. So from here we can conclude that E, this is internal energy of the system. This is a function of entropy S and volume V. Definitely, because by changing these parameters, the internal energy of the system is changed. Okay. Next we have from the mathematical relation of H. Next, from the mathematical definition of H, which is enthalpy of the system. We know H equal to E plus PV. So on differentiation we have dH equal to dE plus PdV plus VdP. Next we have to write down all these relations. Next we can write from here dH equal to substituting the value of dE from this relation number 3, we have D equal to TdS minus PdV. We can write here TdS minus PdV plus PdV plus VdP. We make these relations from equation number 3 by equation number 3. Okay. Now cancelling out these two terms, we have dH equal to TdS plus VdP. This is also very important relation, dH equal to TdS plus VdP. We can name this relation as equation number 4. Now from the definition of Gibbs free energy, now from the definition of Gibbs free energy, gives free energy, we have G equal to H minus Ts. We know this is the mathematical definition of gives free energy, G. Now taking the differential, we have dg equal to dh minus t into ds minus s into dt. Okay, now substitute the value of dh in this relation. We have dg equal to tds plus vdp minus tds minus sdt. Okay, now these two terms cancel out, gives us dg equal to vdp minus sdt. This relation is very important one for different competitive exams like NEET, JEE मेंस, JEE एडवांस्ड. इस रिलेशन तो हमेशा ही आते हैं एग्जाम में. ओके, दिस इज आवर रिलेशन नंबर 5. नेक्स्ट we have another thermodynamic parameter which is Helmholtz free energy, and from the definition of Helmholtz free energy, Helmholtz free energy, we have A equal to E minus Ts. E means internal energy and temperature and entropy. Now differentiating the terms, we know we have dA equal to dE minus TdS minus SDT. Now substitute the value of dE here. We know dE equal to TdS minus PdV. This is your minus TdS at minus SDT. So these two terms cancel out, gives us dA equal to minus PdV minus SDT. And this is again very important term, very important equation, and this is your equation number 6, and from here we can write A equal to function of V and T, and again from this relation we can write G equal to function of P and T. Now we can list up the 4 important relations which we have. The relations are dE equal to TdS minus PdV, dH equal to TdS plus VdP, dG equal to VdP minus SDT, and dA equal to minus PdV minus SDT. So these are very important four relations. These are very important four relations. We just list up these relations. Okay. Now we know if phi equal to function of x and y, and if phi is a straight function, then d phi will be an exact differential. This will be an exact or perfect differential. Exact or perfect differential. And perfect differential होने के कारण it will hold the relation del square phi del x del y. This will be equal to del square phi del y del x. That is, the order of differential can be changed, and it will give the similar result. So we can use all this relation for all the four thermodynamic parameters, because all are state function: internal energy, enthalpy, gas free energy, and Helmholtz free energy. All are state functions. So dE, dH, dG, and dA all are perfect differential. So we can apply this relation for all the four perfect differentials. Now we can do one by one. First one, dE equal to TdS minus PdV. So definitely E is a function of S and V. Now first take the partial differential of del E at constant S with respect to S at constant V, gives us only T, and since V is a constant, so PdV term is 0, dV term is 0. So del E del S at constant V gives us T. Now if we differentiate this one by V, keeping temperature constant, this is del E del S at constant V, and this will be done at constant entropy, gives us this one gives us del T del V at constant S, isn't it? This one is T, and it is differentiated with respect to volume V, del V at constant entropy. That is del T del V at constant S. Again, we first differentiate this term del E del V at constant S. This will gives us del V at constant S. When S is constant, so ds equal to 0. So this one gives us minus P. And now differentiating this one with respect to S gives us del E del V at constant S. This one is V. Gives us minus del P del S at constant V. So since E is a perfect differential, so these two terms will be equal. So this one is actually del square E del V del S, this one is actually del square E del S del V. So these two terms will be equal, and इसके कारण these two terms will be equal. So we'll have the first Maxwell relation. This is, we will have the first Maxwell relation. The relation is del T del V at constant S. This will be equal to minus del P del S at constant V. So this is our first Maxwell relation. This one is known as first Maxwell relation. We have this relation from the function internal energy. So this is the first Maxwell relation, and we have to derive the other relations one by one. Now we can write the Maxwell relation over here. First Maxwell relation, this is del T del V at constant S. This will be equal to minus del P del S at constant V. This is our first Maxwell relation. Next, we have dH equal to TdS plus VdP. So we can write definitely H is a function of S and P. S and P. Now first differential, take the differential of del H with respect to del P at constant S gives us, when S is constant, this term is 0, so this one give you V, and then take the differential of this term with respect to S. So del H del P at constant S, keeping definitely pressure constant, gives us del V del S at constant P. So this one can be written as del square H del S del P. This one will be equal to del V del S at constant P. Now secondly, take the differential of del H del S at constant P. This will be equal to, keeping pressure constant, so dP term is 0, gives us only T. Then del P, differentiate this term with respect to pressure. So del H del S at constant P, and for this differential definitely S is constant, gives us del T del P at constant S definitely. So this one can be written as del square H del P del S. This one will be equal to del T del P at constant S. DH also is an exact differential. इसके कारण these two terms are equal, and as a result these two terms are equal. So this one gives us the second Maxwell relation. We can write del V del S at constant P. This is equal to del T del P at constant S. This is our second Maxwell relation. We can make a list here. This one is del V del S at constant P. This will be equal to del T del P at constant S. This is the second Maxwell relation. Then we can move to the third one, third Maxwell relation. Now the third Maxwell relation is dg equal to the third thermodynamic relation is dg equal to vdp minus sdt. So obviously G is a function of P and T, definitely pressure and temperature. So we can take the first differential of G with respect to P at constant T, gives us T constant, so this term is 0, gives us only V, and then del T of del G del P at constant T. This differential is done at constant pressure, gives us del V del T at constant P. Okay. Next one. Take the differential of G with respect to T at constant P. When P is kept constant, this term is 0, gives us minus S, and then del P of del G del T at constant P. Temperature constant for this differential gives us, there is a negative sign, minus del S del P at constant T. And obviously these two differential are equal because G is a perfect differential. So we can write, since del square G del T del P equal to del square G del P del T. So this one is equal to this one and this one is equal to this one. So obviously the two right terms will be equal. That is del V del T at constant P. This will be equal to negative of del S del P at constant T. So this is a third Maxwell relation. We just list of here del V del T at constant P. This will be equal to negative of del S del P at constant T. This is our third Maxwell relation. And lastly, we have to move to the fourth one. Now we have the fourth thermodynamical relation of Helmholtz free energy, dA equal to minus PdV minus SdT. So definitely A is equal to function of V and T. So we have to take the first differential of A with respect to V, that is del A del V at constant T, gives us T constant. This term is 0, so this is your minus P, And now take the differential of del t of del A del V at constant t. This differential is done with respect at constant V, gives us minus del P del T at constant V. So definitely this one is equal to del square A del T del V, del T del V, this one equal to minus del P del T at constant V. Again, take the differential of del A at with respect to T at constant V, gives us volume constant, means this term is 0, gives us minus S, and then del V of del A del T at constant V. This differential is done with respect to at constant temperature, gives us minus del S del V at constant T. And obviously this is del square A del V del T equal to minus del S del V at constant T. Exact differential होने के कारण these two terms definitely are equal, so this term equal to this one. So we have the relation, two negative sign cancel out. We have the relation del P del T at constant V. This will be equal to del S del V at constant T. So this is our fourth Maxwell relation. Del P del T at constant V equal to del S del V at constant T. So we have the four thermodynamical relations, Maxwell relations. These four are known as Maxwell relations. These are very confusing relations, definitely. They are looks to be confusing. So we have some rules, some mnemonics rather, to memorize these relations. I just you understand the mnemonics. Now the question is how the Maxwell relations can be memorized. These relations looks very confusing, so we have to memorize these four relations. Question is how. Now look at here, there is a square and the four corners of the square contains four different parameters. This is entropy, pressure, temperature and volume, and here it is your H. H means enthalpy, gives free energy, Helmholtz free energy and internal energy. Now importantly, this H is placed between S and P because H is a function of entropy and pressure. Now G is placed between pressure and temperature because G is the function of pressure and temperature, and so also Helmholtz free energy depends on volume and temperature, and internal energy depends on entropy and volume. So these four are placed at the middle of the edges of the square. This square is actually known as thermodynamic square. This is known as thermodynamic square. This is actually thermodynamic square. This is actually thermodynamic square. This is known as thermodynamic square. Now, this square can be memorized in this manner also. It is a mnemonics actually. It can be memorized in this way. We are starting from here. This is G, G, P, H, S, E, V, A and T. We are starting from here. Good professors have studied under very fine teachers. Good professors have studied under very fine teachers. Why it is F? Because it is a free energy term. This is Helmholtz free energy. So this is actually F. So good professors have studied under very fine teachers. G, P, H, S, U, V, F and T. So we have to memorize these four relations from this thermodynamic square. Question is how? ध्यान से देखो, we can divide this square from here. We can divide from here. So there are two parts. There is upper part. This is bottom part. So from here we can write. This is your S and this is your V. So we can write del S del V, and we are it is rotating anti-clockwise. So S and V. So S V and the next term is T, which is present diagonally with respect to S. So del S del V, this is the constant term, this is T. This will be equal to del P del T. Now we are rotating from here to here, PT, and the next diagonal parameter is V. So P to T to V, we are rotating clockwise. So del P del T at constant V. This is the first relation. So del S del V, there is a negative term, and del P del T, there is also a negative term. So this term, this relation will be positive. So we can verify it from here. Del S del P. Del S del V at constant T, del P del T at constant V. So this is our relation. The fourth one is the first one here. So next we come to the next relation. How can we find the next relation from here? The next relation from here. Okay, look at here. Look at here. Next, divide V, the differential term of V, by S. So we can write del V del S. Now we move V to S. This is clockwise manner. Then the next diagonal parameter is P. So del V del S at constant P. This will be equal to del V del S. We have to we divide del V by del S, then we divide del T by del P. We can write del T del P TP, and next anticlockwise, then the constant term will be S, which is present diagonally with respect to the first term. Del T del P at constant S. And again look at here. Del V del S, this is a negative term, and del T del P, this is a negative term. So this term will be positive. So we can verify it from here. Del V del S at constant P equal to del P del S at constant T, constant H. So this is our relation. So this relation is actually this one, and this relation is actually this one. So we can find the two Maxwell relations from this thermodynamic square. Next we have to find the other two. we have to divide the square by a vertical line like this. Okay, now we can find the another two relations. Next, now we divide S by P. This is our dividing line. So del S del P, we can write del S del P, and we are starting from here. Del S del P, this is clockwise turn P to T, so this is our constant term, del S del P at constant T. Del S del P at constant T, this will be equal to del S del P, so equal to del V del T. Del V del T, so we are turning from here to here, so the constant term will give the opposite vertical from the starting point V to P, so this is a constant term, del V del T at constant P. Now look at here, del S del P, this two are negative, but del V del T, this V and T are positive term. So definitely these two are negative and these two are positive, so there will be a negative term. This will be a negative sign. So this is our third Maxwell relation. We can verify it from here. Del S del P at constant T, this is equal to minus del V del T at constant P. This is our relation. This is our third one. This is our third Maxwell relation. And lastly, we have to find the last one. Now we have to divide del P by del S. We have to divide del P del S, del P del S at constant what? Constant, we are starting from here. Del P del S, this is anti-clockwise turn. So the next term will be V, which is present diagonally opposite to the starting point. So del P del S at constant V, this will be equal to del T. This is the term del T del V. We are starting from here, so it is clockwise turn. Del T del V at constant S, which is present diagonally from our starting point. So del T del V at constant S, del T del V at constant S. Look at here again, del P del S, these two are negative terms, and del T del V, these two are positive terms. So there will be a negative sign. This is our fourth thermodynamic Maxwell relations. We can verify it from here. Del P del S at constant V equal to minus del T del V at constant S. So this is our fourth Maxwell relation. This is our fourth one. In this way we can memorize the four Maxwell relations. So this is all about our lesson today. Thanks for watching the video.